Welcome to lesson 4.7. Now we're going to look at inverse trigonometric functions. We've in the past looked at inverse um, functions, other algebraic functions, specifically with log and exponential functions and stuff like that. But now we're going to apply that logic of inverse to trigonometric functions. So a few objectives here. We're going to understand and use inverse sine functions, cosine functions, and tangent functions. And then we're going to use a calculator to evaluate inverse trigonometric functions, and then find exact values of composite functions with inverse trigonometric functions. So we're going to look at how to do the ones you can do by hand first, and then we'll look at the calculator for everything in between. And then there will be some composite functions where there'll be like a trig function of a trig function. We've done composite functions before algebraically. Now we're going to look at that concept trigonometrically. All right, so here are some helpful things to remember from our earlier discussions on inverse functions. When I say earlier discussions, I mean when we did that in Algebra 2, Algebra 2, or I guess some of it was probably beginning of this year as well. If no horizontal line intersects the graph of a function more than once, the function is one-to-one. It has an inverse function. If the point AB is on the graph of F, then the point BA, just flipping the x and the y values, is on the graph of the inverse function. And then we note the inverse function using that -1 exponent. It's not an exponent of -1, it's a sign, a symbol for inverse. Right? The graph of f inverse is a reflection of the graph of the original f function about the line y equals x. So that diagonal line y equals x, it flips it over that because you're flipping the x and the y values of every point. Skip on. First, we're going to look at the inverse of a sine function. The first thing we're going to look at is that horizontal line test that we just talked about. Obviously, a horizontal line will cross a sine function at more than one place. So it's not one-to-one. So you cannot get the inverse of a sine function the entire thing. We have to restrict the domain to a certain part of it. So we're going to look at it from an x value of -pi/2 to pi/2. So from here to here, basically half of a period. Okay. The inverse sine function is noted by sine inverse. So again, that's not an exponent of -1. It's the restricted sine function for specifically a domain of -pi/2 to pi/2. So y equals sine inverse of x is the same thing as saying sine y equals x. You're flipping the x and the y, just like we learned inverse functions did that in Algebra 2. And we read this y equals the inverse sine at x, right? Y equals the inverse sine at x. You can also see that notation called arc sine. We're not going to use that in this lesson, but that is something you could see in other places. So graphing the inverse sine function. Right, one way to graph that is to take points of the restricted domain sine function and just reverse the order of the coordinates. And that's exactly how we did it in Algebra 2 when we were taking the inverses of some algebraic functions. You find the original function, find the ordered pairs, just flip the x and the y, plot those. So this is really no different. All right, so if this is the sine function between, again, an x value of -pi/2 to an x value of pi/2. So this is the regular sine function. We're just going to flip the x and the y. So 0, 0 is still 0, 0, but -pi/2, -1 now is -1, -pi/2, and pi/2, 1 is now 1 pi/2. Another way to obtain the graph of that is just to reflect the graph of the restricted sine function over the line y equals x. So if you have in red there the original sine function, again, just in that restricted value, in that restricted range. You're just reflecting it over that y equals x line. And that's what you're getting in the blue. If you're being asked to find exact values of sine inverse of x, what you're going to do is make a table of values of the, well, these are the table of the key values, right? So we go from negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, 0, and then all those positive as well. Again, this is a table of the original sine function values. This is essentially straight off of the unit circle, although we are going backwards to some of these negatives, right? Okay. So it's half of the unit circle, right? And half of it is backwards. But anyway, these are the points that you already knew about the sine function. So if you're being asked to find the exact value of sine inverse of root 3 over 2, what we're going to do is rewrite it as, just flipping y and x. If I can find what the sine theta of root 3 over 2 is, that will give me the x value. So essentially, if I want it root 3 over 2, I look at my sine function table. Root 3 over 2 is here at pi over 3. So that means the angle in that range, whose sine is root 3 over 2, is pi over 3. So that means sine inverse of root 3 over 2 is pi over 3. So it's giving you the length. Basically, like if you take the inverse of it, it's going to give you the angle, right? So again, the answer to that would be pi over 3. Same thing. Why don't you give this one a try and pause, but just look at that exact same table, and then what is sine inverse of negative root 2 over 2? So find negative root 2 over 2 on the table, and then see if you can find the angle that it came from. So I'll give you a couple seconds to try that. I'm not even going to pause here. Okay, so again, you're looking at this table, you're looking for negative root 2 over 2. Negative root 2 over 2 comes from an angle of negative pi over 4. So sine inverse of negative root 2 over 2 is equal to negative pi over 4. If we're looking at the cosine function, same thing. It's not one-to-one, right? You could draw a horizontal line and touch it more than once. So we need to have a restricted domain for this. For cosine, we're going to go from an x value of 0 to pi. So again, half a period. The inverse cosine function, denoted by cosine inverse, is the inverse of the restricted cosine function, specifically for that restricted domain of 0 to pi. So everything we talked about with the sine function, the inverse sine function, is going to work the same for a cosine function, except the range that we're looking at is a little, I'm sorry, the domain that we're looking at is a little different. So again, if you just look at the cosine function from 0 to pi, you can get these 3 ordered pairs. You flip the x, y values, all 3 of them are going to change, right? So now you've got, instead of 0, 1, you should have 1, 0, which is here. For pi over 2, 0, you now have 0 pi over 2, so that's here. And then pi negative 1 is now negative 1 pi, which is here. Notice how this one's a little different in terms of it actually basically made it do a phase shift when you took the inverse, right? So the domain of the original was 0 to pi. The domain of the inverse is now negative 1 to 1. The range of the original was negative 1 to 1, and now the range is 0 to pi. Notice how the range of the original is the domain of the inverse, and the domain of the original is the range of the inverse. And that's because we flipped x and y by finding the inverse. All right, so same thing. If we're going to find the exact values of the inverse of the cosine function, we're going to get a table of the cosine function values. And again, we're just looking at that restricted domain from 0 to pi. So these are the key values. Cosine inverse of -1/2. I'm looking for -1/2 on that chart and finding what angle that -1/2 came from. So the cosine of 2 pi over 3 is equal to -1/2. So that means the cosine inverse of -1/2 is equal to 2 pi over 3. All right, so now third part of the objective, we're looking at the tangent function. All right, the horizontal line test shows that the tangent function is also not one-to-one. So we're going to have to look at a restricted domain again. We're going to look at between -pi/2 and pi/2. All right, this actually works out to be a full period for what it's worth. So the inverse tangent function is denoted by tangent inverse. And again, we're looking at the restricted domain from -pi/2 to pi/2. Yeah, that's about it. Same thing as before. We take those ordered pairs. -pi/4, -1 becomes -1, -pi/4. 0, 0 is 0, 0. And then pi/4, 1 is now 1 pi/4. And again, domain and range flip-flop because x and y flip-flopped. Finding exact values of tangent function is going to be just like finding exact values of sine and cosine. We're going to have the table of tangent values. And let's see what this example is asking us to find. Tangent inverse of -1. So now we're looking for -1 on that chart and finding what angle it matches up with. So -1, if the tangent of -pi/4 is -1, then tangent inverse of -1 is equal to -pi/4. All right, so these are the graphs of the three basic trigonometric functions, the inverse of the trigonometric functions that we've looked at so far. So you've got sine, you've got cosine, and you've got tangent. So the method that we just went over for those three works really well when it's those specific values. For anything else, you're going to use a calculator. So a couple examples here, cosine of negative, I'm sorry, the cosine inverse of 1/3 is equal to, well, round it to 1.2310. You would never try to do that by hand. Tangent inverse of -35.85 is equal to -1.5429. Depending on what calculator you have and what you're using, there's different ways to do this. If you can't figure out how to do this on a calculator, then jump on a breakout room instead of me trying to go through what it looks like on a bunch of different calculators on this video. I think just give it a try with whatever calculator you have. And then if you can't figure it out, then that's what the breakout room is going to be for during class today. All right. So just some properties. Notice now we're getting into those composition functions, right? If you take the sine of the inverse sine of something, it's going to equal that something. We saw this when we were doing composite functions with inverse functions algebraically, right? If you basically put together two functions that completely undo each other, then you're going to end up with what you started with. I didn't mean to do that. So that works the same whether the inverse is on the outside or the inside, and it works the same for sine and cosine. The only difference is what the domain is, depending on what you're starting with. All right, so cosine of inverse cosine of 0.6 is going to be 0.6. Same thing with sine here, with cosine. Tell you what, I didn't mean to have that. I meant to have those slides in opposite order. So I want to talk through these, and then those other three, I'm going to leave as an exit ticket. So I apologize. Those slides are out of order. Anyway, all right, cosine of inverse cosine of 0.7 is 0.7. All right, sine inverse of sine pi is equal to 0. And that's because sine of pi is equal to 0. And then down here, negative 1.2 is not included in the domain of the inverse cosine, so it's not even defined. Okay. So that can happen as well. So you have to make sure the original, what's on the inside, is in the domain. All right, so like I said, I'm going to leave those other three as part of your exit ticket that we'll do together tomorrow. So let me know if you have any questions. Jump in the breakout room, especially if you need help with the calculator part. Otherwise, exit ticket and start practice tomorrow.